Hello, everyone. This is my talk about the Neo Geo, or at least the work I'm doing on it. I run a small company called BackBit, which makes hardware for vintage machines. Currently, I do it all myself, but might need some help soon. Okay, so this is the first product that I ever worked on for BackBit. When I was really just getting started with electronics, you can see the breadboard. Some board, someone who calls himself Dorktronic made the board. I bought that on eBay as a breakout board. And then I used a Arduino-like device called the Teensy. And then I made my own PCB. And then this is the next version of that cartridge. I called it the BackBit Pro cartridge. And I upgraded from the Teensy to a STM32 microcontroller. And then it's got the pin edge there, which attaches to adapters that can then run in not just a Commodore 64, but any 6502 machine, any Z80 machine, these other machines from the 80s. It's the Fairchild Channel F. There's like a Signetics processor inside the Interton, and some NEC processor and the Epoch Super Cassette Vision, and so on and so on. And so these are some of the adapters that will adapt the cartridge to go into any of these machines, and there's like almost 40 of them now. And so I'm just going to go over a brief overview of what the BackBit Pro cartridge does. And this is something I talked about in my talk last year here. So it emulates ROM and RAM. It supports, I'd like to say it supports all the good ones, all the good systems from the 80s, but maybe some of the more business-like machines it won't connect to. But for playing games, it's pretty versatile on anything that's 8-bit. And even systems that were 16-bit but came out in the 8-bit era, like the Intellivision or the TI-99. The cartridge itself is limited by memory because it uses memory internal to the microcontroller, which is it's a little more than a megabyte, but it's a megabyte that can be accessible by the cartridge. And it's limited by wires, so there's a 16-bit address bus, 8-bit data bus, and some control signals. There's less control signals on some adapters because it uses some of those pins to tell the cartridge which machine it's being plugged into. And so here's the first real limitation of the cartridge, and this is kind of what led to thinking about other projects. I can easily talk to a machine, most machines running at around 4 megahertz, so that's around 200 nanoseconds of latency. But once the latency goes down, so the Atari 7800 has a chip called Maria, which is the graphics chip. And that runs, I believe it makes data requests around 7 megahertz, like half the NTSC rate. And it's possible for me to serve data to it, but I really have to cram for optimizing ARM instructions to do that, because it's using polling to serve data. And so I'm able to support all the original titles on the Atari 7800, but some of the homebrews don't work with this adapter, and that's because the logic becomes more complex when banking gets used, and I just can't optimize the instructions fast enough to emulate every style of banking. And so this is when I started to feel like, I wish I could do better. So one of the things I added to some of the adapters was a PIC coprocessor. The reason I picked PIC was it's different than STM32. I just wanted to try on a different kind of processor. And so I'm using that on the MSX to emulate the sound device present on some cartridges, which is called SCC. It's a very small wavetable. It's like a 32-byte wavetable, so you get these very short loop sounds. It's kind of like playing mods on an Amiga almost. And then Also for the 7800, I was able to emulate the Pokey sound chip using that same processor. And then on the Aquarius, I was able to emulate the AY8910 sound chip, also called the YM2149. It's a square wave sound chip. And then on the Odyssey 2, I was able to emulate the voice, and I didn't even need the PIC coprocessor for that. Because the machine runs so slow, I was able to code enough ARM instructions to just output a signal to a DAC present on the adapter, like a serial DAC with like 6 pins. So I was able to extend the functionality, beyond kind of the original capabilities of the STM32 microcontroller, but I wanted more. So I decided I had to get into FPGAs. So over the last year, basically, I've been trying to do things with FPGA, trying to find the right project that's something that maybe can't be done with a microcontroller or would require a much faster microcontroller, but why not just use FPGA instead? I never got into like Raspberry Pi. I know that's a very popular thing, but as soon as I moved from Arduino to STM microcontroller, I just wanted to architect everything around that. So this is an adapter to go from the BackBit cartridge to the Famicom. And so I stuck some bus transceivers and an additional RAM chip, because the NES, it's like a regular 8-bit, it's a regular 8-bit machine like times 2, because there's the CPU bus and there's also the PPU, the picture processing unit. And so the BackBit cartridge itself only has enough signal lines to do the CPU, and this extends that to be able to connect that RAM chip to the cartridge, to the Famicom to serve it the graphics it needs. And also the FPGA is able to manage different mappers potentially, but I only ever got around to implementing one, the basic mapper, so I could play the 48K Super Mario Brothers. But I never went beyond that because I realized, it was fun to get to this point to make something that could play some games on the Famicom. But you look at the EverDrive clones on AliExpress for like $20, and it's like, okay, well, it's a hard bargain to compete with. So it just seemed like it wasn't going to be really worth the effort to try to go and implement all the mappers, and plus there's a lot of parts on this adapter, and the adapters are supposed to be simple and cheap, and so that's why this remained a prototype. So then my next FPGA prototype was going to be called the BackSid 2. So the SID is the sound chip for the Commodore 64, and I had already emulated that with a STM microcontroller on a product I called the BackSid, which I don't sell anymore, which I don't know if anyone cares if I open source because there's so many other options. But the advantage to doing that with FPGA is that it's cycle accurate. So instead of the sound coming out around 30 kilohertz, it can go the full 1 megabyte sampling rate of the system. So the square waves are a little more crisp. It can even support 2 channels at the same time. But I didn't move this beyond a prototype because the FPGA that I'm using, it's called ICE40. It's not great at doing things like filters because it doesn't have built-in floating point. So the STM microcontroller I'm using actually has better it has a floating point processor. And the way the data is moving, it's going into the microcontroller and then flowing to the FPGA. And the reason it does it that way is because the microcontroller is 5-volt tolerant, whereas the FPGA is not. So I just stopped working on it because I realized filters would be too difficult to get working as good as the original BackSid, so I just decided to stop there. And I figure there's already a lot of SID clones, so kind of like the previous thing, there's kind of too much to compete with to make something really compelling and better than what's out there. So the next prototype I made was the 7800 cartridge, which is essentially the original BackBit cartridge with the adapter just built into the same board. And then it also has, similar to what I did for the Famicom, it has RAM and level shifters built in on there so that it can serve So it can support homebrews that are like 1 megabyte of code and 1 megabyte of graphics. But I never fully implemented it because I just realized there's other pretty good options out there, like the 7800 game drive. And I don't know, I just don't want to be spending the rest of my life selling Atari 7800 cartridges. Forgive me. So next, I think Keith will like this, the Virtual Boy cartridge. So I made this. I was able to get some games running on it. There are, as far as I know, no other ST-based card solutions. I think someone on the internet is promising one, and they haven't quite delivered yet. But my biggest frustration with this is it's got a proprietary connector that you can't get anymore. Someone in Canada, I think, made a reproduction one, but he charges quite a bit for just the connector. So just looking at the financials of it, just didn't seem like it would make sense. And also, the case has to be really, really small and thin, and I just didn't think it was going to be something that would come out nicely with 3D printing. So for those issues, I decided not to proceed. I know Keith still really wants it, so I mean, the option's not closed, but it's just I'm one person and I can do so many things, and to get this off the ground, I would need someone to help out kind of more on the manufacturing side of things. Okay, so here we are. Why Neo Geo? On the left, you can see an original Neo Geo cabinet, but that's not actually what I work with. I work with just a small little harness that goes inside the bottom of the machine. It's called an MVS unit. And then the other one you see here is the AES, and that's like the home console version. And I'm not officially supporting that yet, but it's something I'm considering. So there's these two versions that are very, very similar hardware, but totally different cartridges. Okay, so why did I get started on Neo Geo? So a year ago, I was here, and a friend of mine named Danny, he said, "Why don't you try Neo Geo?" And I was like, "That's a weird idea." And I thought, that just seems kind of crazy. And but here we are. And everyone knows arcade games are the best games, right? All this vintage computer nerds, right? Because the home versions of most games are scaled down from the arcade versions of games. Well, I should probably change that. The original version of a game is often better. So I thought this would be a challenge. It's like 10 BackBit cartridges in one, sort of. There are Neo Geo cartridges available, but there are some things they don't do. Like one thing is most of them take a long time to load a game, like a minute, unless they have the game already loaded into Flash. So if you want to load like King of Fighters 2003, and then you want to load Garou Mark of the Beast, and you want to switch between them quickly, you either have to have those there's like, I guess there's a cartridge that has like 4 flash slots, but if you had like 5 or 6 different games, and you wouldn't be able to fit them in the flash slots. And so this is a solution where you can, so I thought I could get things done faster than a minute to load a game. There are also things that, as far as I know, no other flash cartridge for the Neo Geo supports, which is the multiplayer link cable, where you can connect 2 machines together and play a game like League Bowling. There's not a lot of games out there, but I figure there might end up being more homebrews if there's an easy way to reproduce them. There is a port on the Neo SD that looks like a link cable, but as far as I can tell, it doesn't work. Yeah, so this is the obvious. Something is wrong with my brain, because who would spend like a year of their life working on this machine? But the reality is it's a good use case for FPGA. There are a lot of challenges compared to what I was doing before that really needed FPGA to make this happen. And so I thought, well, what a great project, because I learn best with projects. Okay, so this is what the cartridge looks like. There are 60 pins. These are your regular 2.5 millimeter or 0.1 inch spacing pins, which are the same as most of the cartridges from the 80s. but there's 60 on each side, and there's also 2 boards. So that's a total of 240 pins. Not all of those have to be interfaced with, but a lot of them do. And then you can see I've outlined here MPU. That's a very similar microcontroller to the one I used on the BackBit Pro cartridge. But then I've got an ICE40 FPGA on both boards. I've got a whole bunch of these PS RAM chips, pseudo-static RAM. I've got a big array of level shifters and a big array of resistors. So that's what I just said. The boards are linked by a flat flexible cable, which I just had hanging around for whatever reason because I was using the same cable in my Fairchild channel F, because if you take like 60 pins and divide it down by 5, you get 12, and there's 11 pins on the Fairchild channel F cable, and it just fits perfectly, and just the way it lines up, it actually, even though it's 5 times the pitch, it actually works as a replacement. So I took that same cable. It's also the largest off-the-shelf flat flexible cable you can get. So that cable links the boards, and so the microcontroller is able to talk to the FPGA on the other board through that cable. And then there's pseudo-static RAM, which I chose because it's possible to implement this in SDRAM, synchronous dynamic RAM, but there's a lot of buses that have to access memory all at once. And the nice thing about the PS RAM is that on the outside, it operates just like a traditional static RAM chip from way back when. So it can serve data pretty quick without having to send it a lot of series of commands. It also saved me from having to get into the realm of high-speed PCBs, which is something that's like over like 25 or 50 megahertz. So there are less electrical issues that I would have to face by not interfacing with SDRAM directly, which has been helpful for me to be able to just focus more on the software side of things, making things work in the firmware and the Verilog. I did actually make a SDRAM controller, but it didn't operate at high speed. So that's kind of why I just said, okay, I'm just going to go with PSRAM. I can always cost reduce later by using SDRAM. The microcontroller reads data from the SD card. It pipelines that data over your 80 bits of data bus to the FPGAs. The FPGAs play the traffic cop, and they're able to control the addressing. And I'm able to save pins on the FPGA because the FPGA doesn't directly interface with the data. The data lines of the RAM chips are connected to the CPU, but not to the FPGA. And so I'm able to get away with, I think it's one of the largest so-called flat pack chips. So there's flat pack and there's ball grid array, and the ball grid array chips are more expensive, and they're a lot more expensive to assemble. And so I was able to get away with like one of the larger flat pack FPGA chips. Okay, so this gets kind of into the weeds and very technical, what all the Neo Geo buses are. It's got a main system clock of 24 megahertz that gets divided down. The main processor is a Motorola 68000. It's got a Z80 coprocessor. So it's actually a very similar architecture to the Sega Genesis, which had a 68000 and a Z80, but it uses them quite a bit differently. The Motorola 68000 has a 16-bit data bus. The Z80 has an 8-bit data bus. There's a chip, I believe, which is exclusive to this machine called the Yamaha YM2610, which has square wave sound. It's got FM sound, and it's also got 2 channels of ADPCM, which I'll say what those initials mean in a second. It's got graphics, an 8-bit bus for 2-dimensional text and tiles, which are used like for a HUD on top of the screen. And then it's got sprites or characters, which is a 32-bit bus. And so if you add all those numbers together, you get 80 bits. So it's not technically an 80-bit machine. I think technically it would be called a 16-bit machine, but I have to serve 80 bits of data from the cartridge. So, okay, so these are the individual buses. P stands for program ROM. It's got a megabyte of fixed ROM that has to be served, which is like very similar to the BackBit Pro. But then it's got a megabyte of banked memory, which actually serves up to 8 megabytes in various configurations. And also in that same memory space, on a game like League Bowling, I have to emulate a chip called the HD6301, which is a Hitachi microcontroller, which is a clone of like the 6801 from Motorola. And that's something similar to what I worked with like on the Vectrex, and I guess that's also similar to like a Tandy color computer. So some of the challenges I faced with this particular bus, the machine needs to see the cartridge there right after starting up. And in particular, if you're on a multi-slot machine, it needs to see it there or it just disables the whole slot. So the cartridge has to start up quickly. And the thing is, my cartridge takes longer to start up than a typical ROM chip. But the solution I went with is that there's a self-test on the Neo Geo, which actually takes a few seconds, and that gives the cartridge plenty of time to start up. I did have an idea to put an extra flash chip on there, so there's something like ROM that can start up immediately, but that came with some other issues, which I'll explain in a minute. And so another challenge, having a bidirectional address bus. So I have very limited pins that I can work with. There's an address bus from the Neo Geo coming in, which connects to the RAM's address bus, except if I get a memory request and I have to translate that address to something else, now I've inputted on the address bus what the Neo Geo is requesting, and then I have to output to the address bus what the RAM wants to interface with. And so doing that quickly, it adds cycles and it adds latency. And so that's still a little bit tricky because there's the issue of latency constantly creeps up when changing around the FPGA equations, which I'll also go into in a second. So then implementing the 6301 processor. So I found Verilog implementations of this processor, except they didn't quite work right because I don't think they exactly reproduced how there's built-in serial I/O to this processor, and I don't think they correctly emulated it because at least from dropping it in and trying to get it to work, it didn't work. So there were about 200 instructions that I had to translate from 6301 code to Verilog, and I combed through it like 10 times just to make sure everything was right. And there were still issues, but they've mostly solved. And then lastly on this bus, there's a lot of signals to control the port access. There's output enable and write enable, which are data being sent one way or the other. And those are multiplied by 2 because there's one to specify the high 8 bits of the bus and the low 8 bits of the bus. And so deciding like which of these I could cut out became kind of an issue because you can cut out a few, but then there's trade-offs. So that was a challenge. The Z80 uses a bus called the M-ROM, which I guess stands for music. It's there to interface with the Yamaha sound chip, and that's kind of all it does on the Neo Geo. And it's got some banked memory. On the Sega Genesis, the Z80 is used frequently for co-processing. It's not typically the case in the Neo Geo just because of the way it interfaces. There's like an 8-bit bus between them, but I don't know, just the way the interrupts work is just not super convenient to try to read data off it. But here's a challenge related to the program bus. If I tried to start the machine with a flash chip that's going to the program bus, then the machine can start right away, but the sound will cut out because the system expects both the program bus and the music bus to be active at the same time. And if they're not, the Z80 can go into a crash state where it's like looping through RAM and interrupts are turned off and it's just stuck. And so I decided against having that extra flash chip to have instant startup for the program ROM because it created more problems crashing the music chip. And there is the obvious solution of just enabling hardware tests to get around that. So then the sound chip uses ADPCM, which stands for Adaptive Differential Pulse Code Modulation. There's 2 buses, because there's 2 kinds of ADPCM it uses. There are 6 channels of 18 kilohertz sound that are, it's 12 bits, but it's some kind of proprietary compression algorithm that I didn't have to deal with directly. But those 12 bits are transferred on an 8-bit bus. And then the other channel is variable. It can go from almost nothing to up to 55 kilohertz, and it's 16 bits. So it's higher quality. It's used for playing like background music, whereas the 6 channels are used for playing sound effects. The challenge with these buses is that they're multiplexed. So there's 3 types of data that go across the bus. There's a high address, a low address, so like the upper 8 bits of the address, lower 8 bits of the address, and then data, and they're all on the same 8, excuse me. See, I can't even talk right when I'm talking about this. They're all on the same bus, so data's going one way, data's going the other way, and there are these control signals that tell you which way it has to go, so latency is really critical, and there's like, changing the bus direction can get pretty tricky just to get it just right and on time. A challenge with this is accessing the PS RAM. One of these audio channels, the latency translates to about like 3 CPU cycles. The other one, it's longer, but then it's so long. The PS RAM, if you tell it to output data for over about 4 microseconds, then it'll just die and stop working. So latency is an issue, but also having something held too long is an issue. The MPX signal, so that stands for multiplex, that signal comes from the Yamaha chip and tells you if it's sending you the address, if it's sending the address or it's receiving data. And that came with some challenges because it's a dual edge clock, which doesn't sound that scary, but for whatever reason, so a normal clock, you'll have so a clock is like a square wave, and you'll have one edge that tells you when you should be doing something, but this is a dual edge clock, and I guess for whatever reason, because both those edges have to be sharp edges, there can be a bit of a high current used from the chip, and so at least in one version of the Neo Geo hardware, they put some inductors on those lines to reduce current draw when the signal changes, and then that creates some distortion on the line. So long story short, I had to add some resistors on those lines to reduce the ringing and distortion, because that was creating some issues. Okay, next bus, the fixed layer. This just specifies the graphics for the characters that are drawn on the screen, or the HUD. And the tricky part about this bus is that the actual screen, the virtual screen, is bigger than the physical screen. So there are hidden characters on the edges of the screen that can be used for banking. And that extends the ability to have like up to 0.5 megabyte of memory addressed by the bus instead of like a quarter of that. A challenge was to be able to draw a loading bar on the screen while it's loading data into the memory on this bus meant that I had to add some extra hardware, like a multiplexer, so that if it's loading a game, it serves characters that are internal to the FPGA, and so it avoids having to access RAM while it's loading data into RAM. Okay, and I think this is the last bus I'll be talking about, the character bus. It's a 32-bit bus, and it has to access it 16 times to generate a tile that's 16 by 16. And It's 4-bit color, so that's 16 colors out of a much larger palette. And so a challenge with this was that I had to put 8 PS RAM chips, because to get the amount of memory that's used by the biggest Neo Geo cartridge, you need 64 megabytes, and the PS RAM chips tend to max out around 8 megabytes. So that's why I have a lot of PS RAM chips. So obviously it's much more complex than the BackBit Pro cartridge. A big challenge was just deciding what signals to be cut, because I couldn't, based on the pin counts of the FPGA and the CPU, everything's maxed out, and I just had to decide what signals are more important than others, what signals can I infer using other signals, what signals are just not that important, and so that's been a constant challenge. Reducing latency is a really big issue, particularly because there are different size versions of the MVS system. There's a version that you can put 1 cartridge into, and then there's 2 slot, 4 slot, 6 slot, so you could put 6 cartridges into a 6-slot machine. But those machines are much bigger. They have a lot more hardware because they have to throttle the bus for every cartridge. So you figure there's 80 pins of data that are all multiplexed between 6 slots. And so there's a lot of hardware in there. It creates additional latency. It makes the power of the machine a little bit less stable. And so that means I have to optimize my FPGA equations quite a bit more. And the issue that I've been dealing with over the last week, it's called metastability. That's when a signal going into the FPGA has not settled on 0 or 1. It's kind of in between. And you think, okay, well, it'll just go to one to the other, and then you can process your equations. But that's not exactly how it works, because in the FPGA, if the input is not a 0 or 1, the output of that gate is also not a 0 or 1. And so that unknown state can propagate down a series of gates. And so then the latency between all those gates, and if you add all that stuff up, it can add up to quite a bit of a cascading problem of latency. And it's really tricky to understand, and it's probably even trickier to optimize against, but I'm learning fast. And okay, so what's next? I have to produce an injection molded case. Part of that is because I am kind of sick of being a 3D printing factory. And the other part of that is that a 3D printed Neo Geo cartridge is possible, but it doesn't look that great. It's a bit rougher on the edges. And also, I like to use ABS, and ABS warps quite a bit. The cartridges are around 6 by 8 inches. The challenge with injection molding is the very high upfront cost. Over time, it's probably not that much more expensive than 3D printing, but everything has to be perfect the first time. So I've spent the last couple months doing a lot of perfecting. I should be able to start that process by the end of the month. And then I want to get the PC board final, because once I send that out to however many 100 customers get the cartridge, I don't want them all to have to return that and start all over. So I'm working out the remaining issues. It's amazing how beta testers can find things instantly that you didn't see. And then a friend was able to let me borrow a 6-slot Neo Geo, which revealed that the latency wasn't good enough to work on that. So I've been working on that, and it's getting better. It's almost there. And by almost there, it means I want to ship the cartridge in April, because I already have pre-orders. So I might go through 1, maybe 2 more PC board revisions just to get everything perfect. And I'll probably cave to peer pressure and make an AES version of this, because there seems to be a lot of demand. And the good thing about the AES is it's basically the same hardware. It's just the character bus, the sprite bus, there is essentially a chip that's inside the MVS hardware that is inside the AES cartridge. So there's just a tiny little bit more processing that has to happen. And so that's basically all I have. Now I'm open for questions. Anybody? Yes?
How many prototype boards have you done at this point?
So I think so there's two boards. There's the program board and the character board. The program board has the P, A, and B buses. The character board has the Z80 bus and the graphics buses. So the character board was easier. That's maybe like 3, 4, 5 revisions. The program bus, I've been calling the boards RC since January, and so I'm at RC4. It'll probably go to RC5 or 6 before it's final. But before that, there was, I don't know, somewhere between 5 and 10 boards. So there's a lot of tweaking, and I mean that's why I've been working on this for almost a year. I mean I only started working on it around maybe like May last year, but the process of getting a new board is like it's pretty quick, but the total turnaround between like diagnosing and making changes and sending the new board is probably about a month. So. But yeah, I have a big stack. I was thinking if I should go through the stack and like take pictures of each, but yeah, I literally have a box about this big of all my old boards. Any other questions? Yes?
The retro boosters that I'm looking for a USB RAM instead of you makes it.
Sort of. So I make a chip tester, and I'm currently working on a new version. But I made this product, I called it the corn bit, because on the Commodore 64, there's a chip called the kernel, and I just thought that because the chip had extra pins on the top and bottom, it sort of looked like a corn cob, so I called it the corn bit. But that was a flash memory chip on a chip with a few extra pins that could be plugged in the chip tester to program it, and that was from an SD card. So it's almost USB. But yeah, it's not a big focus right now because it's a lot of effort to build those things. Anybody else? Yes?
What's after Neo Geo?
What's what?
What's after Neo Geo?
Oh God. I don't know. The focus is gonna be Neo. Oh well, I mean, this guy wants Virtual Boy. The chip tester. So I have my so-called version 3 of the chip tester, which compared to version 2, it adds level shifters. It adds what else? Analog inputs. It adds a drop-in module for being able to test chips, different voltages. So that's probably like my main focus after Neo Geo is just finishing version 3. Like the hardware is done, I just need to give it a case and do some testing. But yeah, I mean like every project I like to do, I like to learn. So I'm probably not going to be selling Neo Geo cartridges forever, and I'm probably going to want to do something else afterwards. So I'm always open to ideas. Yes?
How do you know when to start taking pre-orders? It sounds like you started taking them even before all the bugs.
Right. So I started taking pre-orders in January, and I had been dragging my heels for a long time because I wanted to get the hardware as perfect as possible. But I started taking pre-orders partially to fund the mainly to fund the product. Because I'd already invested a lot of time and money in it, and my other products seemed to be selling a little bit less, so I did need money to support continuing working on it, and I also need money to start the expensive processes like the injection molding, and to pre-order parts, just in case there's a shortage on the parts. And so I really dragged my heels as long as I could, where I was just like, okay, I really have to move forward on this. And the pressure actually really helps me to get things final. Like, once I announced pre-orders, I realized there's a lot of people who could help me beta test. And then because I have pre-orders, now I can make a whole bunch of beta cartridges that would normally be like, oh, I don't want to invest in this, but now I can. So yeah, I mean, really, that's like my policy is like to drag my heels as long as I possibly can before I'm like, okay, I really need, a little bit of kickstarting here to finish the project. Yes?
Do you ever prefer level chips?
The one I'm using on this is Texas Instruments. I go to Texas Instruments a lot for various chips. They I don't know, they're kind of like the gold standard with something that just works well and is also really cheap. But the level shifters I'm using, you have to specify the bus direction. I know there's some where the bus direction is like automated, and a bunch of people told me like don't use those because they're not as reliable. Yeah.
The main trouble with them is that the time it takes them to figure out which way they're driving just significantly increases your latency.
Yeah, I mean latency is everything because there's latency at every stage. There's latency at the level shifters. There's latency in the FPGA, and it's like all that adds up. And you could compare that to the architecture in the original cartridge, which is typically like a custom gate array inside the original cartridge, which I'm kind of replicating, but I'm also actually adding a lot of parts because that original gate array would be 5-volt native, and it wouldn't have to talk to a bunch of other chips. Like everything's on that one chip, and they designed the silicone to do exactly what they wanted, whereas I'm using off-the-shelf parts. I'm not designing my own silicone yet. I would say long-term, that's probably my biggest ambition. Long-term is, someday I'll maybe make my own silicone, so that might be fun.
I'm curious about how much reverse engineering you have to make versus how much documentation you will find because of this architecture.
There's a heck of a lot of documentation on neogeodev.org. There's a few hard-to-read PDF scans of old Neo Geo schematics and documentation. So I've used everything I can, but having this active community of people who want to share what they've discovered about the machine has been really helpful. But it also takes a bit of grokking to decipher that. So I mean, there were a bunch of border revisions I made just to support titles that have certain banking implementations where it wasn't obvious right away, even with all the wikis out there. And so I had to go through a bunch of border revisions to figure, oh, I actually need this pin, and I actually need this other pin. And I've also relied a lot on MAME emulation source code, which has been really helpful for the encrypted ROMs. Because if MAME can play it, then it's been deciphered. But there's a couple situations where even MAME doesn't quite get it perfect because MAME can change the hardware. I can't change the hardware that it's plugged into. And so that leads to more like what a MiSTer would do. Yes?
Have you ever considered working in the Naomi system cartridges?
What is that?
Also, the arcade system that runs either cartridges or they have a GD-ROM, which is a CD and DVD player that load from the DVD into the system. So basically, it's a cartridge system.
Not yet.
It's similar to the one of the other Sega Genesis, some of the newer Sega, the Dreamcast. You share a similar software hardware.
The nice thing about the Neo Geo is that it's like a 90s system, but I figure the hardware probably was designed a few years before the system came out, at least much of the hardware. So it's a little bit evolved from the 8-bit system, so I'm kind of working my way through the eras slowly. I mean, it's really nice having those large dual inline package chips because that's something I can relate to right now. Any other questions? Or I guess we're out of time. So thank you for coming, and I'll be here all weekend.